Today we are going to go over the singular value decomposition and the principal component analysis and also the dimensionality reduction. Now these are powerful techniques used in data science and machine learning to simplify complex data sets. So for example, SVD or singular value decomposition is a mathematical method that decomposes a matrix into three distinct components, revealing its underlying structure and helping to analyze patterns within the data. PCA, or principal component analysis, is a statistical procedure that leverages SVD to transform the data into a set of orthogonal components, capturing the most significant features while reducing noise and redundancy. Dimensionality reduction in general aims to reduce the number of variables or features in a dataset, making it easier to visualize, interpret, and process without losing essential information. These techniques are widely used in fields like image compression, natural language processing, and data visualization to enhance computational efficiency and reveal hidden data relationships. So we'll go over these topics in detail next. So let's imagine a 2D set of points. It's possible that we might rotate the main axis or the principal axis this way to make them all project into a 1D points. So essentially these 2D points are really a set of 1D points if you can reduce the dimension from 2D to 1D. Now think of a 2D object with dots on the surface as a cylinder-shaped object. The points are in 3D, but if you flatten the cylinder into a 2D paper, all points remain and maintains the original variance across the points. That's another example of dimension reduction. Without losing much of the variance exist within the points, we were able to reduce the dimension, in this case from 3D to 2D. Now let's take a look at this data set. What does a close inspection tells us? There are only two distinct vectors that defines the nature of this data set. I can mark it up here by using, if you look at this component here and this component here. Those are the only two things that are very, very similar to in its nature. But we cannot observe them easily. Let's go back to the highlight here. Yes. All right. So but we cannot observe this easily in a large data set. We need some tools from linear algebra. So we define what's called a rank of a matrix. The rank of a matrix is the number of linearly independent rows that cannot be represented as a combination of the other vectors. Now, if you look at the rows of this matrix, you can see that this second row can be a combination of the first row because you can just multiply the first row by 2, you get the second row. Third row is the same as the first row. The fourth row is the same as the sort of 5 times the first row. Same thing here. Once you have this any one of these things, you can get the other ones because you can just do a multiplication there. And this, therefore, the rank of this matrix is 2 because you only have 2 linearly independent rows in the whole system. In other words, that's the only thing that tells us the story of what the structure of this matrix is. The basis is the minimum number of rows or columns needed to span the vector space. For example, if we can construct any 2D matrix with 4 matrices of 2D matrices of dimension. So think of something like 1, 0, 0, 0, and then 0, 1, 0, 0, then 0, 0, 1, 0, and then 0, 0, 1. So if you take those 4 basis vectors, you can form any 2D matrix. So therefore, the dimension of that space is 4. The rank of a matrix is the largest number of linearly independent rows or columns in a matrix. So in this case, we're asking you to find the rank of the matrix generated by the vectors. So in other words, you have to find the number of linearly independent vectors of this set here. So the way we are going to do that is to form a linear combination of the vectors a times 1, 1, 0, b times c times, set it equal to 0, and we get a plus 2b minus c equals 0, and then a plus b equals 0, and so on. So we get only two equations because there's no equation coming from this one here. So if you solve these things, this implies that a is minus b, and then b is equal to c by plugging a equals minus b into this. So the relationship between a, b, and c are clear. There's only one variable that we need because a is minus b and the b is minus c. Therefore, b can be represented from a, c can be represented from b, and therefore they can be represented with a. Hence, these vectors are linearly dependent only. So this kind of shows you why that's the case, right? So otherwise, if they are linearly independent, we should get 0 for all. So there are some guidelines for handling missing data in a data set. We suggest that if a row or column contains too many missing entries, especially say over 90%, or if the data is deemed insignificant to the analysis, that row or column should be removed. The process of removing rows or columns not only cleans the data set, but also reduces its dimensionality or the rank of the matrix. By doing this, the resulting data set becomes smaller, making it easier to store and process, and which enhances computational efficiency and facilitates more streamlined data analysis. This also says that if you remove a row or column, it also reduces the dimension, and the reduced dimension sets are easier to store and process and do the computation. So in this case, the applications of dimensional reduction. So if you can find we describe a technique for optimizing data analysis through dimensional reduction, like it highlights the discovering hidden relations among features of topic, like identifying phrases that frequently appear together in former President Donald Trump tweets, is "Make America Great Again." Or it can provide a deep insights into the data, the whole data set here. And the process involves removing redundant or unimportant features, which are sometimes just noise and do not significantly impact the analysis. So reducing the dimensionality of the dataset makes it easier to store, process, visualize, and interpret, enhancing the clarity and efficiency of the data analysis. So here we try to describe the concept of dimensionality reduction in terms of projecting data points from a higher dimensional space, in this case 2D, into a lower dimensional space, in this case 1D. We raise the question of which direction has the maximum variance, highlighting the principal components provide the answer. For example, the first principal component, denoted as U1, represents the direction with the highest variance in the data, capturing the most significant information. The second principal component, which is U2, which is orthogonal to U1, accounts for the next highest variance, providing additional insights while maintaining independence from the first component. This approach is the fundamental component of principal component analysis. In this case, if we go from a two-axis, the original one, into rotate and get two x-axis, you might decide that we only need the first principal component because the second component really has not much variance preserved if you map these points into the second principal component. So let's do this workshop. Let's say that we have a point with respect to x-axis and y-axis. That we can express the point as 1, 2 with the standard basis vectors 1, 0, and 0, 1. So 1 is really the coefficient of the first basis vector. 2 is the coefficient of the second one, which is like the y-axis. If you think about it, this is like the x-axis. Suppose that the axes are rotated counterclockwise by 45-degree angle to get the axis x prime and y prime. So something like this. Let me just draw it here to slow it down. So they have that the original axis here, and then you rotate them by 45 degrees counterclockwise, so you get new axis here. So this is 45 degrees. Okay, so the thing is that this 0.12, which exists somewhere here, let's say this is 0.12, I think the question we're asking is, what are the coordinates at that point with respect to the new set of axes? That's what we're trying to solve here by trying to express 1, 2 in terms of the new basis 1, 1 and minus 1, 1. So this is 1, 1 and this is minus 1, 1. So again, we go through the solving the equations. 1 is equal to A minus B, and 2 is equal to A plus B. By solving them, you get 3 half and 1 half. And then we say that the original point with 1, 2 with respect to the standard basis, for the new axis, those coordinates are 3, 2, and 1 half. So essentially, now we can use a new set of axes with different coordinates for the points. All right, so let's. So our goal in any data analysis project is to preserve as much variance as possible in the original data set by projecting data into a new coordinate system using dimensionality reduction. So we explained that if the data has D features, and the aim is to project into a linear subspace of much lower dimension, say P, and the P is what we wanted to find out. While the data doesn't have to lie exactly on this lower dimensional subspace of dimension P, it should be close to it. The vectors that define the new coordinate system, which are fundamental to techniques like principal component analysis for capturing the most significant features of the data set. So next on to SVD. So consider the example of developing a movie recommendation platform to explain the benefits of singular value decomposition. We illustrate that with a large table showing user preferences for movies, SVD can help uncover hidden patterns in the data. So it can identify groups of people with similar tastes and reveals that similarities among movies. So by breaking down this complex data into its most important components, SVD allows the system to make more accurate recommendations, even for movies a person hasn't seen yet. The simplification of data enhances both the system's efficiency and the user's experience. So we provide a mathematical definition of SVD. We explain that the SVD is a factorization of the original matrix into 3 different matrices, U, S, and V transpose. But this S matrix is a diagonal matrix with non-negative numbers on the diagonal, which we call them singular values. And U and V are orthogonal matrices. They are orthogonal matrices because if you take U times U transpose, you end up with the identity matrix. More on that from the linear algebra videos you can find. The matrix S contains, which is a diagonal matrix, contains the eigenvalues of this XX transpose, which are called the singular values. So when you take the matrix X and factorize into 3 matrices, it looks something like that. So the matrix S contains the eigenvalues of A transpose along the diagonals, and then it's possible to show that SVD exists for any given matrix A, and the matrices U, S, V are unique, and diagonal entries of S are ordered from largest to small. In some readings, U has dimension M by R, S has dimension R by R, and V has dimension N by R. So you will notice that if you take U, S, V transpose, you get an M by N matrix. So let's think of an image compression application use SVD. Let's say we have an image, in this case my image, that we consider as a matrix. And note the color images are stored as 3D matrices where the third dimension is the color of any pixel denoted by red, green, and blue. It's a 3D vector. So let's suppose we split the image into red, green, and blue matrices, images. So it means we have now 3 images of this size. And then we do SVD on all 3 matrices. Then we get rank 1 representation of the red, green, blue and put them back as matrix. So we note that if you do rank 1 matrix, rank 1 approximation, which requires not just 3 vectors or 2 vectors and one singular value, you're going to get some level of an approximation to the original image. Now, if you add more vectors, let's say we add 3 vectors here, rank 3 matrix, we get something of some kind of a shape of the image. So we can recognize that this is an image of a person. Here we just see the colors. And then if you go to rank 10, which means that we get 10 or 20 matrices and 10 singular values, which is much less than the original set of vectors, we get something very close to the original thing. So what's the point here? We can actually represent the original image as an approximation using just 10 vectors and 10 singular values. So this is a reduction in size to represent the original image. An example would be that if you're sending images from satellite to Earth, we can send just a few vectors first to see if the image is useful. So in this example, we take a movie rating matrix where rows are the users and columns are the movies. And we can do SVD on this matrix. And we'll get 3 matrices, U, S, so sigma in this case, and V transpose. So U is a 7 by 2 matrix, and sigma is a 2 by 2 matrix, and then V transpose is a 2 by 5 matrix, which are like, you can see that it's a 7 by 5 here, so the product end up with that. So the SVD shows us that there's only 2 important components in this matrix. Those are the 2 latent features. Now, if you look at the inspect the matrix, you notice that it seems like these are very similar and these are very similar. So that means we might identify there are 2 themes here. Those themes are the aliens and the sci-fi movies and the romantic movies. Now, keep in mind that although we are showing this in a nice way, this can all be scrambled and we may not be able to notice this relationship across all these movies. So that's the point. Now here's an example of actual SVD on a matrix. We take a matrix and use some kind of NumPy or something to find the SVD factorization. It gives you this factorization here. Now if you look at the numbers here, this is 12.48, which means that the sci-fi concept perhaps has more weight, and this is 9.5, right? That's like the romance concept, but the rest are really 0, so you can just ignore them, I mean almost 0. So there are no other concepts. This could be this is sort of like noise. You can consider this to be noise. So you only need 2 of these things to really make a determination. Another application of SVD is what's called the latent semantic analysis. So we introduced this as a technique used in natural language processing. So LSA involves analyzing matrices of word occurrences. So if you assume that these are the documents and these are the words, within a collection of documents. So we have a collection of documents, we have words and the documents. So it's going to examine the relationship between documents and the terms they contain, ultimately producing a set of concepts that relate to the documents and terms. So this method helps uncover hidden patterns and the meaning of in-text data, making it useful for tasks like information retrieval or text summarization and topic modeling. So in this case, we have 3 documents and 4 words we consider. The SVD factorization gives us U, S, and V transpose. In the orthogonal matrix V transpose, each row represents a topic and each value represents the weight of that topic. So here's an example of an animation that I will demonstrate to you that if you look at this matrix, you have a bunch of documents here and the words within those documents. And the color indicate that color indicates the density of the word in that document. Like for example, blood occurs a lot in the document 4. So let's put this into action and see what happens. So this is going to go through some level of matrix transformations. It's going to shift rows and shift, in this case, it's shifting columns and rows. You can see that. And then what happened here is, if you now notice, it actually put the matrix into a very nice form, where if you look at this group of matrix documents, D0, D14, D15, D8, that contains the mostly on these words here. So you might discover that this is the sort of the environmental theme that we are looking at in this group here. In this group of documents, we are likely dealing with immigration. So that's another set of things. And here, we are likely dealing with this set of documents here. We are likely dealing with space and shuttle program and so on. And there's a lot of noise around here, drug blood study, those documents, but they are really not a clear group of things like this one. But here you might say this is about the defense, these documents D6, D13. So what we are saying is that by doing SVD, we might identify within these documents there are 1, 2, 3, 4, 5, maybe this may be a half a theme. So let's say 4.5 themes in this document. So that's an interesting one. All right, so this is the code that is used to find the SVD. You can carefully pause the video and look at it, how it's done. You have an array. You call the SVD from NumPy, SciPy, in fact, linear algebra package, and you get the USV transpose. And the approximation, reconstruction of the matrix can be done using this. So, for example, we take the array, we take the original matrix. Let's say you want to compute the rank 1 term. So we take the first column of U, reshape it to be a 3 by 1, and the first column of V transpose, reshape that to be a 1 by 2, and the rank 1 matrix is then formed by the first singular value, which is S0, this column vector U, and the row vector V. And the error, meaning that rank 1 is an approximation to the original matrix, so the error is going to be the difference between these two things. And you might expect this error to be large because it's just a very simple approximation. If you compute the rank 2 term, you go through the same thing. The first column or the second column of U, second column of V, and reshape it and then form the rank 2 term. And if you take the rank 2 minus A, it gives you the rank 2. But typically what we do is we combine the rank 1 and rank 2, which will give you less error than rank 1 error or rank 2 error. So error with 2 singular values. So if you keep finding several ranks, rank 3, rank 4, and so on, if you find all the ranks and add them up, it's actually the original matrix. So as you add more rank components, the error goes down. But the point is that you want to know how many rank components do we really need, and do we really make sense to collect. That's the point. So this is kind of showing you that idea in the image reconstruction. So here's a rank 1 approximation. I'm using a vector of 300 dimension, 200 dimension, and then times 3. That would be the number of colors in there. Plus 4 bytes, which is to get the one singular value here, which is like an integer. Rank 2 matrix approximation is 2 of those, and then plus 2 singular values, 3 singular values, and 4 singular values, and 10 singular values to get the rank 10 approximation. So as I go from here to here, you will notice that the image becomes clearer and clearer. In the lab, you can actually do any image you like to do, construct this kind of operation. Now, in my own work, we introduced this notion of SVD in a 1998 publication called Interactive Linear Algebra with Maple, published by the Springer Verlag. So we ask you that you perform these operations and do this lab. And let's get to the principal component analysis next. So principal component analysis is a technique for transforming a set of observations with possibly correlated variables into a set of linearly uncorrelated variables. It says that if there are n observations of d dimension, then the number of principal component is going to be minimum of p or n minus 1, where p is the rank of the n by d matrix. The first principal component is the largest possible variance, so that has the most significant thing. Now, if this component is much higher than the others, you can just ignore all the others because there's only one dimension that you need to represent this thing. The goal is to maintain this data variance as much as possible during transformation to a lower dimension. So another example of PCA is that given a set of tweets, we can take all the tweets, so think of tweets as documents and the words within the tweets, and then you have these colors again indicating the density of those words within those documents. So the idea is that if you take this matrix and do principal component analysis, you might find that there's themes like Make America Great kind of come together. That's kind of an interesting way to think about that. So SVD and PCA are two eigenvalue-based methods used to reduce high-dimensional data sets to low-dimensional data. So both methods retain the information or the variation of the original data. So this is kind of showing you we have this original data, the blue dots, and then by rotating the axis, we find a principal component like that. So we can find a nice principal component here. Let's wait till the gets to the next place. It keeps going. Now here we have, okay, so this is now we're getting there. So that's one component, and there's the orthogonal component to that. So to find PCs, we could go through this process. Suppose A is an n by d matrix with n observations and d features. Assume that A is centered, that is, the mean of each column is subtracted from all the data in the column. So that means each column mean is 0. Now we construct a covariance matrix C by using A transpose A dividing by A. So that's the covariance between the variables in this matrix. So the covariance matrix is a symmetric matrix because A transpose A is a symmetric, meaning that Aij is Aji. Now the covariance of two variables is defined by the xi, xj is defined by the expected value of the deviation of xi from its mean and the xj from its mean. We'll get to that in the probability sections. So if you have any symmetric matrix, say C, then that can be diagonalized as VD, V transpose, where D is the diagonal matrix with eigenvalues in decreasing order. V is the matrix of eigenvectors. These eigenvectors are called the principal axis or principal directions. So let's go through finding PCA and SVD. PCA is projections of data onto the principal axis are called the principal components. The jth principal component is given by AV, where V is the matrix defined in this A transpose A factorization. We call that the covariance matrix. The coordinates of the ith data points is given by the ith row of this product matrix. So you can also get the PCA from SVD. We find the SVD of a matrix A equals US V transpose. And then we form the covariance matrix A transpose A over N. Because now A is US V transpose, we can do matrix operations to, so this is the transpose of that. So you get V transpose transpose, S transpose is the same as S because it's diagonal, and U transpose. And then you get the US V transpose, which is A, divided by N. And then because U transpose U is I, you can just ignore that. That's like the product one. And then we get V times S squared over N V transpose. So the singular vectors V are the principal directions and singular values. And the eigenvalues of covariance matrix are related by that. So in this case, once you find the singular value decomposition, you can take A times V, which gives you the principal components, right? So here's, you can do this workshop by finding the PCs using the following SVD decomposition. All right, so that's the end of this.